Hey guys, so in this R help session, we're going to be talking a little bit more about dummy variables as well as interactions. And in this session, we're going to be using data from GitHub. So go onto GitHub and download this Diamonds Reduce CSV. And there's no direct download button, so what you need to do is to click on the raw right here, copy the URL, and then you're going to put that basically right there in this command. So I'm just going to paste it again. It's the same thing. I'm going to run that. I renamed my file to my data to diamonds just so it's a little bit shorter, but it's up to you. So I'm going to run that. Okay, so just to show you what the data looks like, just right off the bat. So there are many different variables. Some of them are quantitative. Some of them are categorical. And in this R session, we're going to be using a quantitative as well as a categorical variable to predict price. So let's just jump right into it. And before we even started, I wanted to kind of give just a very quick recap on dummy variables. So usually when you do regression in R, it's always quantitative, but R cannot always do it if it's categorical. So when you have to add a variable that is categorical, that's basically a dummy variable. So R automatically creates the predictor or the dummy variables for you. And the number of predictor variables is always equals to n minus 1, where n equals the number of levels. So if you look at the data set, let's say for example for cut, you can tell that there are 4 different levels. There's excellent, there's good, there's very good, and there's also ideal. So later on I will show you once we run the regression that there will be 4 minus 1, aka 3 predictor variables that R will create for you. But I just wanted to get that out of the way right up front. And the one level that is not included in your output will be the reference level. And I'll go through that in more detail later on. So, okay, let's go into the coding part. So, first off, we kind of want to get a little bit more of a better sense of what our data looks like. So I'm going to do a plot command. And in this case, we have chosen caret size as our quantitative variable, so this one. So we're going to run that, and you can tell in the plot right here that there is one outlier, and that will probably significantly affect our regression output. So what we want to do is to basically get rid of this outlier for the purpose of this discussion. So what you want to do is to run this command right here. This basically means that, using my current data set of diamonds, since this is what I named it early on right here, I only want you to include data points where caret size is less than equals to 3. And the reason why I chose 3 is because you can tell past 3 there's basically no more, it's only this data point. So everything else less than 3, you basically want all of this. So, I gave it the same name because I don't want to change my data set name again. I'm going to run that, and just to replot it to show you what the new plot looks like. So now you can tell that the points are, much more spread out, and you don't have that outlier right there. Okay, so in class, I'm going to kind of follow the progression or the way that the professors went through this in class. So first off, I'm going to build a model with just the caret size, so just the quantitative factor. So, same way of writing your model as you have learned so far. I'm going to name it model 1, and then I'm going to do predicting price from caret size, and then you need to tell R where your data comes from, so data equals to diamonds. Okay, so I'm going to run that, and if we look at the R square, it's pretty good at 76% right now. So just keep that, at the back of your mind. And then next, you're thinking, okay, hey, maybe does cut also can cut also be a predictor of price? You think about it like, hey, maybe I think it does, because if you have a different type of cut, that may lead to more expensive or cheaper prices. So I'm going to add that variable to my model. I'm going to run that model 2 and make a summary. And as you can see, the R squared did increase a little bit. So after you've done this, you can, sometimes you want to see if caret size as well as cut has an interaction with each other. So basically, does it mean that, what if the value of cut could affect the slope of caret size? Or what if the value of caret size could affect the slope of cut? And before I kind of delve deeper into this, I wanted to give a quick example from your slides, just to kind of ease our way through this. So in class, there was an example, a regression that you guys ran, basically predicting the prices of houses from living area as well as whether or not they had a fireplace. And the one thing that is very important to note is that, for houses with a fireplace or without a fireplace, ultimately you're not going to affect the slope of living area. And why is that so? The reason why is because when there is a fireplace, since this is the dummy variable that R created for you, when there is a fireplace, you're going to enter 1 into this variable. So ultimately, you'll be left with 5, 5, 6, 7. And that number is just a numeric number, so there's no variable left. So that's only going to affect your intercept ultimately. And same thing with when there is no fireplace in the house, because when there is no fireplace, you put 0 for the value of that variable. So this becomes 0. So this multiplied by 5, 5, 6, 7 will be 0 multiplied by that will give you 0. So ultimately, it will only affect the intercept. So just to keep that in mind. So when you have that, the slopes of the two levels, aka fireplace, when you have a house with a fireplace versus when you have a house without a fireplace, the slopes are going to be the same, but the intercepts are going to be different, as I've just mentioned. So now that you kind of remember that, this part of the code, I just want to say first that you probably will not have to know whether or not to, So for this part of the code, it's basically, we kind of wanted to walk through with you guys to tell you to see if you can figure out whether or not you need an interaction term or not. However, in the exams, I am about 95% sure that you will not need to know whether or not you need an interaction term. Basically, your professors will tell you in the questions, build an interaction term. But we just kind of wanted to go through this just to show you the thought process that you should have, when doing your project, because you might have to do this during your project or in real life, later on, how to see whether or not you need an interaction term or not. So the idea here is that we are creating different models for every level of cut. So as I mentioned just now, under the cut column, there's excellent, there's good, there's very good, and there's ideal. So we did that right here. So creating a model for every level of cut that the diamond could potentially be. So this is basically the same kind of code that you guys have learned before already. So essentially, you're building a linear model, but only taking data from, when the cut is excellent, when the cut is very good, etc. And then we're going to build the models and label those models. And now we're going to plot all these models onto the same scatter plot that we did, right up here. So I've copied that same plot command down here. So first off, I'm just going to run all these to create the models. And then after that, I'm going to run this command as well. And so that gives you that plot. And these 4 commands basically tell you, I want you to print the regression line onto this plot that I just ran. So I made it different colors just so it's easier for you to kind of see the slopes and the point that we're trying to get across. So I'm gonna run that. Let me expand that really quick. So as you can tell, the slopes are different for different levels of cut. So if it's excellent, it's different from very good, which is different from ideal, which is different from good. So if you look at the plot right here, you can tell that the lines are pretty well spaced out here. But then when you go towards the other end, you can kind of tell that the spacing, has kind of shifted. So that means that the slopes are different. And recall what I just said a little while ago is that if terms kind of have the same slope, then you can kind of maybe think that you may not need an interaction term. But since the slopes that we just observed are different, then it's more likely that there could be an interaction between the variables, because now you're saying that, for example, the level of cut could affect the slope of caret size, and the value of caret size could affect the slope of cut. So having done that, we are going to build an interaction model. So here I have model 3, same thing, just that we're replacing the plus sign with a multiplication sign. So we're going to go ahead and run that. Okay, and then let's go ahead and look at the summary real quick, because I wanted to talk you guys through the coefficients and how to interpret them. So okay, I just wanted to make a little note here that the code below here is not actual R code. I just wanted to kind of type out the regression equation for you to see, and you'll see why I did that in just a second. So let's look at this particular coefficient right here, this particular variable. So these, this is your usual caret size x variable, and then you have the main effects as well as the interaction effects. So let's kind of delve into it. So let's say you're looking at this coefficient, at this variable right here. When your cut is equals to good, so when your cut is good, aka this right here, and just to say, if you're starting out and you feel like you don't really understand how to read or interpret the coefficients, the easiest way to do it is to write out the entire equation, and it will become very clear to you. And after a while, if you're able to get the hang of reading coefficients, then you can do it the shortcut way, which I will show you right after this section. So, okay, so jumping into it, so I basically just wrote out the entire regression equation without the coefficients, because they're all right here. So just to kind of go through it, -1579, that's your usual intercept, and then this is beta 1, beta 2, beta 3, and so on. And then you're going to put the respective variable next to their coefficients. So this is basically writing out the entire equation based on the output that you have here. So bear in mind that right now we're looking at when cut equals to good. So when cut equals to good, as I mentioned earlier when we were talking about the fireplace example, when you have a fireplace, you put 1 into that variable, and if you don't have a fireplace, you put 0. So looking at this is the exact same idea. So my equation will kind of be reduced to, my intercept will still be there. My caret size is a totally separate variable, so we're just going to keep it as it is. And as I mentioned before, cut good will ultimately become 1, but let's just write out the usual, the normal equation as of now. So beta 2 as well as the cut good variable. And then beta 3 and 4 are going to be 0, because when your cut is equals to good, that means that all other cuts are not possible, because your diamond cannot be of cut good and of cut ideal at the same time. So this will be 0, and 0 multiplied by, beta is going to be 0. So this is 0, that is 0. You're going to want to keep beta 5 as well as this interaction term, because cut good is in it, and you know that cut good could possibly affect the caret size. So you want to keep that in your equation. But same idea for beta 6 and beta 7 as well as these two variables. Since this is talking about how cut ideal as well as cut very good could affect caret size, it's irrelevant, because right now you know that you're just talking about when cut equals to good. So, beta 3, beta 4, beta 6, and beta 7 all become 0. So the equation is basically reduced to just that. And like I said earlier, when your cut is good, you want to put 1 into that variable. So I'm going to replace my beta 1 with my coefficient right here. And then for beta 2, for cut good, you can see that the coefficient is negative 456. So I'm going to go ahead and put that and multiply that by 1. And then beta 5 for caret size and cut good, you're going to look here, and that is your coefficient. So I'm going to put that there, as well as that's going to be 1. So you're going to be left with caret size as your variable right here. And then once you shorten the equation, you're going to basically get that. So for this basically means that off a diamond of cut good, an increase in 1 unit of caret size, this is just how you would usually interpret your normal regression equations. An increase of 1 unit of caret size is associated with a 6,133.5 increase in the price of a diamond of cut good. So that's the long way to do it, but it's also a very safe way. But once you get the hang of it, basically all you have to do is, it's the same idea. So if you look at the output right here, you're looking at cut good, so you don't care about these two at the bottom, and you don't care about these two right here, because those are irrelevant. So looking at this, when your diamond is of cut good, the slope of my caret size will increase or change by this amount plus this amount. And the reason why we have to look at both is because you're saying you have to take into account both the main effect as well as the interaction effect. So this is the main effect and this is the interaction effect. So you're saying that for a diamond of cut good, my caret size the price of my diamond could increase, for every 1 unit increase of caret size by negative 262.9 and 6396.4. And that, when you add that together, that basically gives you the 6133.5, which is the exact same thing as we did, that we got when we drew out the entire equation. So that's one interpretation. But as I mentioned earlier, this kind of goes both ways. So the value of cut good could affect the slope of caret size, and the value of caret size could affect the slope of cut good. So now we're going to go on to the other interpretation, which basically says that, if you have a diamond of, just to kind of backtrack a little bit, remember how I said earlier, when R gives you all the predictor variables, it will give you n minus 1. So in this case, our reference level will be excellent, since this is the only one that is not available in our output. So looking at that, a diamond of when we look at this coefficient, we're basically going to compare that to the reference level of excellent. So when of a certain caret size, when your caret size is a certain number, a diamond of cut good, basically this is going to tell you what, how much more or less is cut good, is a diamond of cut good going to be worth compared to a diamond of cut excellence. So looking at this again, it's basically the same coefficient, but now you have to look at the main effect of cut good, which is negative 456.0. So this is the mean effect, and this is the interaction effect. It's the same idea. But yeah, so just to repeat myself, basically when your caret size is a certain number, so whatever it is right here, and you have to include that in your interpretation or your calculations, because the very fact that this is an interaction variable is telling you that caret size will play a part in the slope of cut good. So you're going to do that, negative 262.9 as well as negative 456.0. So this means that a diamond for a given caret size, whatever you specify in your caret size variable, a cut good will be worth 262.9 plus $456.0 less, since it's negative, than a diamond of cut excellence with the same caret size. So this is the proper interpretation for it. And yeah, so those are the two interpretations that you should take note of. And I kind of want to go back to this command right here, ANOVA. ANOVA basically tells you the significance, the statistical significance of your categorical variable as a whole. So if I'm going to run that really quickly, so you can see right here, looking at my interaction term, the p-value is pretty high at 0.21. So if you compare that to the usual alpha level of 0.05, this is, statistically insignificant. So basically this tells you that even though we thought initially, because the the slopes of the lines were different, that there could be an interaction term, R is telling you that no, this is not a statistically significant variable. So in terms of the interaction, so the interaction is not a statistically significant variable, so it's not worth it to have this as an interaction term. So you might as well just go back to this. So yeah, that's basically all I have to share in this R session. If you have any other questions or you're not sure about certain things, do feel free to come to my office hours or any of the other TA's office hours as well. We're more than happy to help you. Yeah, so thank you for listening to this.